Okay, what we're going to talk about today is, oh yeah. Okay, what we're going to talk about, we're going to finish up chapter 3, a quiz. Is it Professor Chiesa or Professor Chiesa? Okay, good. Like bruschetta, right? Yeah, okay, we're going to talk about this. At the end of his lecture, I saw that he said that if you want to topologically sort, you just output an ordering that gives you topological sort is the inverse post ordering. Okay, so it's going to take me a little while to get there because to prove that it's a little bit there's a little bit of stuff that needs to happen, so I'm going to go a little slow. But he did say that. I'm going to go through a few slides. I may go quickly. Slow me down if you have questions. But we'll get to this notion. The local target is topological sort. A topological sort is the inverse post order. Okay, from DFS, depth first search. Okay, so we have graphs. Their edges. Here you have a tail, you have a head, right? It points from, for this edge, AB. An edge, again, is a pair of vertices. And in directed graphs, the edge goes from the tail to the head. Okay? We saw depth first search. Any questions? That's okay? Okay. So this is explore. This is a recursive procedure. You see the recursive call? Does everybody see the recursive call there? What's the data structure that's associated with the recursive procedure? A stack. Okay, so there's a stack somewhere here. We didn't really have to write it with recursion. We could have done it explicitly with the stack, right? In some sense. Okay. So for Professor Chiesa and I, we were chatting in the office. We were thinking about the stack. We were talking about the stack. When we talk about depth first search, you visualize stuff coming in and off a stack. Okay, so that's what's happening in this recursive call. You're exploring V. V is on the stack, and when you explore W, W is on the stack. Okay, and you explore W from V only if there's an edge from VW. Okay, you're only calling explore W from explore V if there's an edge there. You're not always calling it. If W is already visited, you wouldn't explore it again. That's really what's happening here. Okay, you set pre to clock. Pre and post is this clock that he was talking about. He talked about this clock with the brackets, and you're labeling the bracket as you output the brackets in this parenthesized version. Okay. And DFS, now this is an interesting procedure too. Why do you even have this? Why don't you just call explore on any vertex? Why do you have a depth first search? When was it useful? He gave you an example where, this doesn't sort of explore the whole graph. For undirected graphs, when doesn't this explore the whole graph? Yeah. Yeah, when it has more than one connected component. Okay, so for directed graphs, it's going to be more complicated. You may call explore. Connectivity is a more complicated object. He said briefly what strongly connected means, but depending on the order of the graph, order of the vertices here, you could have many calls that are here, or one call that's here. Okay, one call to explore in the main routine. Okay, the runtime is V plus E, and he argued. Last lecture that this is a recursive algorithm, but do not try to analyze it using Master's theorem or anything like that. Okay, you analyze this algorithm by just watching it and saying what does it do, and what you in particular do is you watch every time it goes through this loop. And what he said is in class is he said that every edge is looked at twice. And you could charge all the other work to that action. Okay? Does that make sense? If you look at all these loops, there's just some work, but you call explore. Okay? And then maybe pre and post visit, those are trivial, but those are all correspond to an invocation of explore, and the work in here corresponds to an edge. You deal with an edge from both ends, and that's it. Okay, so the total work is just, you look at it and you sort of analyze where the work is by understanding this flow, right? We didn't use a recursive analysis, right? It's a big step, actually. It's kind of cool. So, okay. Terminology. Okay, so now when we, with this view, the root, I'm going to use some words. I want to make sure you understand what I mean by those words. Starting point, it's when Explorer is called directly here. This would be a root if you called it here. Okay? V is an ancestor of W. V is on the path from or to a root, okay? Depending on which order you're doing it, okay? V is on the stack when exploring U, if you want to think about the stack. So when we think of depth first search, we think about the action of a stack. We're pushing stuff on, we're taking stuff off. Okay, we're thinking about recursion that way. Really, that's why it's not really recursive. Recursive has this magic thing, you just explore and something happens and it's all nice. But here we're actually looking at the stack. The recursive is just a convenient way to express it. Okay, V is a descendant of U, that's obvious, it's the opposite of ancestor. Okay, so here's a directed graph. And let's look at depth first search. Let's just execute it. Okay, so let's just put post-order numbers and pre-order numbers. So that'll be a pre-order number. And now what is it going to do? It's going to put one of its neighbors on the stack, right? I guess it chose B and puts down the pre-order number and so on. It chose D. D chose C. C looks at B. And why is that colored blue? What's different about the red ones and this blue one? In the procedure. We're not going to call explore on B again, because B was already visited. Okay, does that make sense? So this is not, the red edges are what we're going to call tree edges, but so on. Now we pop it off. There's nowhere else. We've explored all the edges out of, we've looked at all the edges coming out of C. We pop, we post, we post, we post. We go on. G has nowhere to go, so out it pops. Pop. Now, I guess that skipped a step. It pops, it goes to A, which then explores and looks at the next edge in this list in that first loop, and goes here, and then F is exploring its outgoing arcs. F looks at D, it sees that D is visited, and I color it. I'm not going to put that edge in the tree per se. Well, the color has a meaning, but we'll talk about that in a minute. 11, okay, and so on. Okay, so you should really have a feeling of stuff coming in on the stack and coming out of the stack and then exploring the outgoing arcs. Okay, now a tree edge, the coloring here is a tree edge or a forward edge. So the tree edges are the ones, when we looked at the edges coming out of A, what we saw is, let me see if I can do the light. Okay. There's some way to do a pointer, right? Okay. So A, we look at the edges coming out of A. If that edge is not visited, we call that a tree edge. Okay. If on the other hand, when we go back to A, we may see F. And we see that F is already visited, but it's still a forward edge. It goes to a descendant, okay, in the tree. Okay, and now we can also see a property here. Now 10, let's look at a forward edge, AF. Okay, let's look at the interval. Okay, these are the intervals of each vertex. And the interval is the pre and the post. That's an interval. And this interval for this vertex is its pre and its post. Okay, so when this interval is entirely contained in this interval, what does that mean in terms of the stack? It means this vertex is being explored. When this vertex is being explored, it starts being explored after previous, and it ends being explored prior to post. And this is the period during which V is on the stack. It says U is explored while V is on the stack. Okay? So that's why it's a forward edge or a descendant edge. Okay? So in this case, the pre and post for F is for F is 10, 11, right? 10, 11. And it's inside the interval of 0 to 13. Okay? A was on the stack for the entire period, 0 to 13. So F was being explored while A was on the stack. Okay? Does that make sense? Okay. Back edge, it's just the opposite. It's, you see a back edge here? Do we see a back edge here? So a forward edge is from an ancestor to a descendant, or a tree edge. So what is a back edge? It's going to be from a descendant to a ancestor. And do you see that anywhere here? C to B. Okay, let's see. Now what I'm claiming here is that V, the interval of V, contains the interval of U, meaning that V is on the stack when U is explored. So what we're saying here in this case is that B, since we're saying that C to B is a back edge, we should say B is on the stack when C is explored. Okay? Does that make sense? And we saw that happening, right? We saw B was on the stack, it explored D, then it explored C, then I colored this blue. Okay? So, and you can also check it sort of just by using the post and pre-order number. The interval, the time when V is on the stack, this interval seems all formal and stuff, but it has an intuitive meaning. It's when it's on the stack. The time when V is on the stack contains the time when U is on the stack. So U points back up to the ancestor. When U sees this edge, UV, it sees that V is on the stack. Okay? Okay, and then now there's this cross edge. That's what happens here is there's one other kind of edge, right? There's the blue edges, the sort of these red edges and the forward edges, which are cyan, I guess. And then there's this cross edge, which is green, which is drawn here. So it says, essentially, this whole subtree over here was explored before F was. Okay? So all of that stuff is no longer on the stack, and F is explored. Okay, so that's what this is saying. Interval of V, the tail, that D is the tail. D is on the stack entirely before U is on the stack. Yeah? Oh, yeah. This means this interval is inside this one. This one means this interval is inside this one. Okay? It's just, yeah, U contained is in V, is what I could have also said. Okay, they're just, yeah, I'm in the house. The house contains me. Okay? Rao is in the house. Okay. Okay, so, yeah. Okay, does that make sense? So this interval, F's interval, is entirely before, here in this case, it's all entirely before this one. Okay, so you just think of these things as times. Okay, I redrew it. These are, again, the edge from U to V. There's a tail, there's a head. The tree edges are direct call. It's just the call tree of Explorer. It's how we get intuition. The forward edge is, here's a forward edge from A to F. Edge to the descendant. The back edge. You see the back edge? Anybody see a back edge? Yeah. From C to B. It's an edge to an ancestor. So it differs from a forward edge. It's from an ancestor to a descendant. This is from a descendant to an ancestor. A cross edge is none of the above. But what but it has F before B. Now, could it have been possible that this edge is the other way and not be a tree edge? No, it would have been explored. Okay, so these are the only possibilities. We could think of an edge where this guy's interval is before this guy's interval, and it's then that doesn't exist. It just doesn't exist. Okay, so not all four cases are there. One interval is contained in the other. That's two cases. one interval is before the tails interval is after the heads interval. That's possible. The heads interval cannot be ahead of the tails interval. Okay, so directed graph. Okay, so without cycles. We care about directed graphs without cycles because we generally want to say hello before goodbye. Otherwise, it's very awkward. It doesn't have cycles, right? So you can order it, right? You can say, okay, with a directed graph, you should say hello before goodbye. Now, if I have some more complicated structure, which is like building my my code, right? This could be building my code. What I'd like to do is build my code in some order. And if there's a cycle somewhere in this graph, I'm out of luck, right? It's hard to build things in some order, right? Where if they represent precedences. Okay, so an acyclic graph. So is this one acyclic? Where's the cycle? Yeah, there's a cycle, right? Everybody see the cycle? Okay. Okay, so now it's harder to see. I mean, you could see it, right? But I just want to pretend that one needs an algorithm, right? So I put in a lot more edges. You still see the cycle? There's still only one cycle, right? I've added everything in a way that I didn't add any, I think. I didn't add any cycles. Okay, well, I didn't add it so that there's no cycles. Why did I do that? Where is it? C to... Okay, okay. Okay, G to C to F to... Okay, I see it. Wow, you guys are good. Okay. That was was it a long cycle at least? Okay, so anyway. So this is, okay, those are the pre and post. Let's run depth first search. Presto bango. Okay, so the back edge, okay, here's the back edge is this. Edge is the ancestor. Okay, so now we want to see if there's a cycle. Now let's look at the back edge. In this case, we know there's a cycle and there's one cycle. Okay? And we see in this cycle there's a back edge. Okay? So, so that's nice, right? The back edge UV, the interval of V contains U, interval of C is 3, 4. It's inside of 1, 8. Why do we know that causes a cycle? We can see it in this example, but why do we know that? If we see a back edge, we know there's a cycle. That's what I'm trying to argue. Why do we know that? Yeah, you should justify that to yourself, right? What do these intervals mean? Now these intervals, instead of the annoying things the professor is just talking at me about, they tell me what's happening, right? I look at the interval, I tell you, look, B is on the stack from time 1 to 8, okay? And that means there's a path from B to C, okay? And C is on the stack from 3 to 4. How did C get discovered? Well, B called explore, and then it called explore again, and then called explore again. At some point, there's a sequence of explorers that put C on the stack, and B is still on the stack. So therefore, there's a path from B to C, okay? And now we also know there's an edge from C to B. If there's a path from B to C and an edge from C to B, do we have a cycle? Yes. Okay, so that's how we know. Okay, so with these intervals, it becomes very easy to say, oh, if there's a back edge, which is trivial to check, you just check the endpoints, the pre and post, and you know there's a cycle. You run depth first search. You don't have to look at the tree edges. You don't have to look at anything. You just look at each edge and you say, well, is it a back edge? Oh, I can tell that just with the pre and post numbers. Now I know whether there's a cycle or not. Is that clear? Okay. So I believe, you know, I'm just putting it in a little bit more careful language, but it's what Professor Chiesa said. Okay? Path of tree edges to V to U because V is on the stack. V's interval contains U's interval. So V is on the stack.